we conclude this session with our second poster lightning talk session, which will last about 20 minutes.
For the past 30 years, Ontario has been processing its single-dish continuum data using an all-command line program called Lines. Lines, unfortunately, has not been maintained for over 7 years. It's based on Fortran 77 and suffers from compatibility issues with some newer operating systems. It requires expert installation, and users are required to manually set up plotting parameters as well as perform raw file conversions each time they run a new analysis. DRAN, the Data Reduction and Analysis Program, was developed to address these and other similar issues inherent in the Lines program. The new program is fully automated and also allows for single-file and user-led or manual operations. It has a user-friendly command line and graphical user interface. It's based on Python and also offers a range of new features like outlier detection and flagging, which were not previously available with Lines. Comparing results obtained using DRAN to those obtained using Lines shows that the two softwares are comparable, and also that DRAN seems to appear to have smaller errors in its fitting routines, implying that it may even be slightly better than the old Lines program, which was one of the goals we wanted to achieve with the new software upgrade. Thank you for your time.
Hi everybody, my name is Tamara Civera and I am Scientific Database and Web Access Engineer at CEFCA. CEFCA is carrying out from the Observatory Astrophysical Javalambre in mainland Spain two unique multi-band photometric large sky surveys, JPAS and J+. The two large surveys include quadrid and individual frame images and catalog data. To publish all of this data, the CEFCA Catalogs portal has been implemented, offering web user interface services as well as virtual observatory services. This contribution summarizes the effort and work made in the CEFCA Catalogs portal to enhance data publication following fair principles, increasing data value and maximizing research efficiency. For example, to make data findable, the CEFCA Catalogs publishing registry has been implemented. To improve accessibility and interoperability, all service data is accessible through BO services which have been validated using EVOA validators and improved to be full compliant. And to improve the usability and provenance information, individual frame images are now offered. But there is still work to do, so we are going to continue working to be more fair.
Concept behind the idea of our plugin: get closer to the realization of three-dimensional sky maps. Three-dimensional information, such as conditional and marginal distance probabilities, are provided for any position of gravitational wave sky maps. As you can see from the video below, for any gravitational wave sky map visible on Aladdin, several SAM connections are set to receive an M-type about the coordinates of the click position of the map, of which the probability distributions along a line of sight are embedded in a TK-Inter interactive window. Thank you for listening.
Hi, my name is Ulrich Amen Busok. I am a postdoctoral fellow at Zurich University. My poster is about accelerating the search of optimal solution intervals using DASC arrays. So what are solution intervals? In most calibration softwares, the user has to set a time and frequency interval for which he assumes the gains are constant. This helps improve the signal-to-noise ratio and better constrain the optimization process. The difficulty is selecting the right solution interval. That is one that's long enough to provide a good signal-to-noise ratio, but at the same time short enough that you can subtract the intrinsic variations in the gains. In our previous research, we found out that in order to have optimal solution intervals, we need to compute them separately per antenna, frequency channel, and data chunks. In this poster, I discuss how this computation can be accelerated using DASC arrays and X-array MS. See you during the poster session and have a good conference.
Hi, my name is Sándor Kunsági Máté and I am a PhD student from Hungary. In our work, we have developed a two-step source separation tool where we can successfully decompose simulated disk galaxies into the young blue and old red stellar populations. We have created a neural network that predicts the two broadband spectral energy distributions, or SEDs, from the color distribution of the galaxy within a mask. The achieved accuracy is 2 to 3%, which is about 2 to 4 times better than using Scarlet. We then implemented the model of galaxy image generation in TensorFlow and optimized this model for the morphology matrices while fixing the SEDs. As you can see, this very simple model provided better predictions for the brightness profiles than using Scarlet. If you have any questions, feel free to ask me.
Well, hello everyone. My name is Landman, and I work in the radio astronomy research group at Sarajevo. My research mainly focuses on improving imaging and calibration algorithms for continuum interferometric data processing. In this edition, I'll be talking about PFP Clean, a distributed imaging library I've been developing in Python. Come and talk to me if you're interested in fast and accurate distributed gridding, or, as my poster title suggests, if you want to know how to use the preconditioned forward-backward algorithm to tidy up after clean. Hope to see at least some of you at my poster. Cheers for now.
My name is Mark Taylor. I have a poster X7008 about a program called TAPlint, which is a TAP validator. I'll run it while I'm talking. TAP, the Table Access Protocol, is a VO protocol which is used for clients to talk in a standardized way to remote databases. It's a complicated beast. It's composed of a dozen or so standards. And so if you're implementing a TAP service, then there are lots of opportunities to get things wrong. TAPlint is a tool which will act as a client and pose lots of queries to the service and check that the responses it gets back are in accordance with the various standards. This is it running, and you can see it just outputs lots of different reports. W means warning. There's something that you maybe should take a look at. Info just tells you what it's doing at the moment, and if there's an E, it's an error that means something's in contravention of the standards. If you're running a TAP service, try running TAPlint against it and see if it's behaving correctly. Thanks.
I want to give you a very brief summary of this poster. This work is part of the post-processing data being carried out in Wallaby survey, where different centers in different geographical locations, such as Australian SRC, Spanish SRC, and CIRADA in Canada, will produce advanced data products publicly in the forum source catalogs, cutouts, or kinematics that have to be replicated in an effective way. Here we develop a model and a strategy to solve this data distribution problem. We validated several services and tools, but finally we decided to use Bucardo as a replication engine. To validate the effectivity, a benchmark has been designed to simulate the production of data and its distribution to the sites, capturing the metrics. The results are clear. Data synchronization and replication is sufficient for the future scalability and remote collaboration needs between sites. That's all. Thanks. Bye-bye.
Hi, my name is Evan Jones. I'm a graduate student at UCLA working with my advisor, Tuan Do, and I want to share with you the data collection process for our project performing photo Z estimation with galaxy images using a convolutional neural network. We use data from HSC to obtain 5-band photometry for galaxies spanning up to and beyond redshift of 4. Cross-match these galaxies with available spectroscopic redshifts, and then input this sample into HSC's image database to obtain images in each of the 5 bands for about 300,000 galaxies. We then process each of these images in Source Extractor to remove background objects from the field and perform a number of quality cuts to finally obtain a data set of about 220,000 galaxies for input into the neural network.
Hello everyone, my name is Jan Grange and today I will be discussing poster X9002. This poster is based on work we did in the ESCAPE project for work package 2. The goal of this work package is to assess whether the infrastructure that is used for data management by some of the particle physics experiments can also be applied to other fields like ours. I will first start by discussing the infrastructure itself, which consists of 3 tools. Ruscio, which takes care of data management and application of rules and policies. FTS, which actually takes care of copying the data between 2 endpoints. And IM, which gives users the opportunity to log in to the system using their institutional credentials. Furthermore, I will continue by discussing some of the differences between our fields, what makes astronomy special for data management. If you want to know more about this, please come to me during the coffee break or have a look at poster X9002.
Hello and welcome to poster X9-005, using script generators for pipeline prototyping. In this poster, I am presenting a solution to a problem which most large observatories face. Big astronomical projects need automated pipelines for data analysis tasks like calibration and imaging. But fully automated pipelines take a long time to develop and require good knowledge of data which is not available at first. So how can observatories still release data quickly to their users after first light or an observatory upgrade? The solution I propose is to use one or more script generators as pipeline prototype. I suggest that this should be done in a three-level development approach consisting of scriptable toolkit, script generator, and finally automated pipeline. I discuss the properties of script generators and finally give a real-world example, the ALMA Observatory, which has used calibration and imaging script generators since 2012. Enjoy the poster and paper.
Hello, I'm Paul Barrett at the George Washington University. I'm the creator of VisFit, which is a Julia programming language package for fitting radio interferometry visibility data. The reason I created this package was because the half dozen applications that are out there I found too limiting. So I developed my own package in Julia, which I consider the successor to scientific Python. It allows me to analyze radio data instead of several days. With typical software, and within a half an hour, typically, I can create light curves and spectra. And it's still in its early stages. It will continue to be developed and should be available from the Julia Package Manager within a few weeks. If you're interested, please take a look at it, provide feedback. Thank you.
My greetings to all conference participants. I am Olga Zhelenkova from the Special Astrophysical Observatory of Russian Academy of Sciences. For a number of years, we have been conducting massive studies of radio sources obtained as a result of a series of surveys carried out with the Ratan 600-meter radio telescope. For this, we use data from all available resources, sky surveys, catalogs, and so on. We were able to identify practically all radio sources with optical objects. The result is a fairly extensive collection. As we continue to work with these objects, we need tools to conveniently work with the collections. We started developing a prototype information system based on Python and PostgreSQL. Now the system web interface displays images and tabular data. In the future, we plan to develop the system functionality.
I'm Alice Allen, editor of the Astrophysics Source Code Library, and my poster is SciCodes, Astronomy Research Software and Beyond. What if you had a research problem that could be solved computationally, but you didn't have the software that could solve this problem? What if a code that would work for you already existed, but in another discipline? How would you learn about it? That's one problem that SciCodes wants to solve. SciCodes is a new consortium of research software registries and repositories from many disciplines and wants to make scientific software more discoverable across disciplines. This would not only help you find useful research software regardless of which discipline it was developed in, but would also help make your own software more discoverable. Want to know more? Please view my poster, catch up with me at ADAS, visit the SciCodes website, or drop me an email. Thank you very much.
In this video, I will show how to use YAFITS inside Artemix. So let's log in and then search for a source, for example, M83 by source name. And you can see all the different observations that have been done with ALMA. Then I will select one project. For example, this one. You can see for this project code you have here, and most ID you have 10 FITS file, and I can open the FITS file inside YAFITS. Then I can select a region here where the signal is. I can do a search to resolve the source and redshift via MED. And then I will display the lines, theoretical line expected, and you can see where are the lines. YAFITS is available via Zenodo. You can download it on GitLab. And if you have any question, please send us an email to artemix.lerma@obspm.fr. Thank you.
Hi everyone, I am Giuseppe Todisco and I'm a research fellow at the Astrophysical Observatory of Catania. I'm here to present the Via Lattea, a visual analytic system that offers a set of tools to study the star formation process in our galaxy. One of the main components is the Via Lattea knowledge base, a collection of datasets and object catalogs. The VLKB offers 2D and 3D surveys, numerical model outputs, and web services for data discovery and data access. The main way to consume the Via Lattea knowledge-based data is through the Visual Analytic Client, an open-source application that combines different types of visualization to perform correlation analysis. If you want to know more about Via Lattea, please contact me during the conference. Thank you for your attention and goodbye.
Hi, my name is Lexi, and I am speaking about a tool geared towards web-based polarimetric analysis called Polaris. Polarimetry means measurement of the rotation of the plane of polarized light. It is an important diagnostic tool because from it, astronomers can learn about the magnetic structure of astrophysical objects such as galaxies and the environments they exist in. But polarization properties can vary across a galaxy, and this means that there is a need to examine different interesting areas on the galaxy, which we call lines of sight, in an attempt to get a clearer understanding of the variation of the magnetic field. Astronomers do this by generating various plots of spectra, and that means plots showing variation of magnetic fields across wavelengths of each line of sight. To have an overall view, they have to shuffle between the lines of sight on the galaxy's image and their corresponding spectra. But what if I told you that there is a way to visually achieve this on your web browser? Polaris does that. Shown here is what its current interface looks like. Want to know how it works? Please see my poster, scan this QR code to interact with Polaris, and contact me if you would like more information. Thank you.